First of all, I would like to thank the organizers for inviting me to give this talk. I was really looking to being there in person, but unfortunately, we live in very interesting times, and due to medical reasons, this was not possible. So I also thank the organizers for their flexibility in the very last moment. So I will talk to you today about the place where I work, CERN, and its mission, challenges that we face, and the future that is ahead of us. So I will kick off with a brief introduction who I am. I was born, raised, and educated in Łódź. I actually graduated from the Lodz University of Technology. And in 2010, I had an opportunity to go to CERN to work on my bachelor's project. And I stayed there ever since. So I did my bachelor's there, my master's, PhD, postdoc, and now I work there as a staff engineer. So currently I am employed as an electronics engineer in the Beam Instrumentation Group of the Accelerator Systems Department. And in my daily job, I am responsible for designing new hardware and maintaining some of the existing hardware of some large measurement systems. So what is CERN? I think CERN is best defined as a European laboratory for particle physics. It is located in Geneva, Switzerland. It's actually just on the border with France. And it's an international organization which was founded in the middle of last century when Europe was still recovering from the devastation of the war. So the conventions with which CERN was established say that the organization shall have no concern with any military work, and all the results of its work should be published and generally available. So CERN took this credo to heart very strongly, and for the last 68 years, we worked very hard to bring science for peace. So CERN is composed these days out of 23 member states. All of them are located in Europe, but CERN has a worldwide reach with several associate member states and observer states located all around the globe. The annual budget of the organization is in the order of 1.2 billion Swiss francs. And CERN is home to around 16,000 personnel. Out of the 16,000 people, 3,500 are employed directly by CERN, and all the rest are employed by their home institutes, one of the 450 collaborating institutes. So as this conference is taking place in Poland, I think it's very appropriate to at least mention the Poland at CERN status. So Poland started its history at CERN quite early on, so less than 10 years after establishment of CERN in 1963, when it became an observer to CERN. But due to the political climate at the time, Poland had to wait for almost 30 years until it could become a full member state. And this happened in 1991 when President Lech Wałęsa ratified an agreement between CERN and the Republic of Poland. And in June 1991, the flag of Poland was actually raised for the first time on CERN site. Poland contributes around 35 million Swiss francs annually to the overall budget of CERN. So this is just short of 3%. And we are represented by around 550 Polish personnel at CERN, out of which 80 are employed directly by CERN, and the rest are employed by some Polish institutes. So there are tens of Polish institutes which collaborate with CERN and hundreds of Polish companies which do business with CERN on a daily basis. So all this gave us very good reputation among colleagues from other nations. And this led to many Poles holding senior engineering and scientific positions in the organization. So what I would like to stress on this slide strongly is that many Polish institutes play really key roles in the existing and future CERN projects. So as an example, I can give the background image of this slide, where the Institute of Nuclear Physics of the Polish Academy of Sciences in Krakow is routinely invited to CERN to conduct some extremely crucial electrical safety measurements in the Large Hadron Collider. So CERN employs now around 3,500 people, with 16,000 people collaborating in total. But it was not always like that. The beginnings of CERN were rather humble. So the first accelerator, which we built in 1957, the synchrocyclotron, it could fit in a reasonably sized building, and it didn't take so many people to maintain this accelerator. However, just 2 years later, we built our first underground accelerator, the proton synchrotron. Actually, this is one of the oldest accelerators that we have at CERN, and it's still operational and is absolutely crucial for the success of CERN until these days. So it's a really amazing piece of technology built 60 years ago. So to give you the sense of scale of this accelerator, here you can see 5 cars parked on a road leading to a central storage and operation and controls building of the accelerator. The next milestone in the history of CERN came in 1971 when we built our first collider, so the intersecting storage ring, ISR. And the nice thing about colliders is that they allow you to smash a beam of particles against another beam of particles rather than a beam of particles against a stationary target. So when you smash 2 beams of particles together, the discovery potential that you have with such collision is much, much higher. So this was really a significant step in the history of CERN. Another very significant moment in the history of CERN was in 1984, when it was the first time that CERN scientists received a Nobel Prize for their work at CERN. So these were Simon van der Meer and Carl Rubbia, who in 1984 received a Nobel Prize for their discovery of the W and Z bosons, which was done just a year before. So for those of you who are unfamiliar with how the Nobel Prize Committee works, in physics it's very rare that you have to wait less than 10 years for your discovery to be recognized. And these 2 gentlemen received their Nobel Prize just 1 year after the discovery. So this just speaks to the significance of this discovery to the physics at the time. So now let's jump ahead to 2010. So this is the first year of the operation of the Large Hadron Collider. The LHC is by far the largest scientific instrument humankind has ever built. So it's a 27-kilometer long ring, which is buried 100 meters underground. So in this photo, this yellow line is actually the outline of the LHC, which is plotted over the French and Swiss countryside. To give you the sense of scale of the accelerator, here you can see the International Airport of Geneva with the city of Geneva behind. And just at the top of the slide, you can see the Alps with Mont Blanc in the middle, overseeing the basin of the Geneva Lake. So the tunnel in which the LHC is built actually hosted another accelerator before, the Large Electron Positron Collider, the LEP, which was built in the 80s. And LEP operated until the end of the century. So I think it was decommissioned in 2001. And then when LEP stopped operation, the tunnel was emptied and the LHC was installed. So the LHC was way more powerful than the LEP. And it's proved its worth in less than 3 years, because in 2013, Francois Englert and Peter Higgs received a Nobel Prize for their theoretical prediction of the existence of a Higgs boson, which was then discovered in the LHC. So all this took only 3 years to discover something which was predicted in the 60s. So such discoveries, of course, motivated us to dream even bigger. And this is exactly what CERN is famous for. So right now we are working on a conceptual design and a feasibility study for the next big accelerator, which we, for the moment, call the FCC, Future Circular Collider. This behemoth will be 100 kilometers long. and it will encompass the entire city of Geneva and even some mountain ranges inside. But this is a story for a completely different presentation. So I propose we go back to the current times, to 2022, and we focus on what CERN has now. So over the last 68 years, CERN built a very vast complex of interconnected accelerators. Some of them are more well-known than the others. I think some of you might have heard, for example, about our antimatter factory, which Dan Brown made quite famous in his novel and the later film with Tom Hanks. But by far, our most famous accelerator is the LHC. So how do we actually get particles into the LHC? It's a very good question. It all starts now in LINAC 4, which is actually the latest addition to our accelerator complex, which was added in 2020. The particles are accelerated along a linear accelerator, and then they go through a succession of bigger and bigger circular accelerators until they arrive in the SPS, in which they are. So the SPS, which is our second biggest accelerator, is 7 kilometers in diameter. And in the SPS, these particles are accelerated to the energies of 450 giga-electron volts. So the SPS is connected to the LHC in 2 points. So it can transfer the particles to the LHC such that they go counterclockwise, or it can transfer the particles to the LHC such that they go clockwise. So with this scheme, we can inject 2 counter-rotating beams to the LHC, which is great for us because we can then collide these 2 counter-rotating beams. So with 2 counter-rotating beams, we accelerate them in the LHC to the energy of close to 7 tera-electron volts. And then they are brought into collisions in 4 dedicated points. So Atlas, Alice, CMS, and LHCb. So the LHC is a real accelerator of records. So the vacuum in the vacuum chambers of the LHC is as empty as the interstellar space, and this is absolutely crucial when you have high energy beams. Now, these high energy beams have to be steered around the LHC, and this requires thousands of really powerful superconducting magnets. These magnets, to operate, have to be kept at temperatures which are colder than the deep outer space. So they require extremely huge cryogenic plants running 24 hours a day. And the particles are accelerated in huge RF cavities to extremely high speeds, which are virtually the closest we can get to the speed of light these days. When the particles are brought into collisions, these collisions happen in some of the most sophisticated particle detectors ever built by people. All these detectors then produce copious amounts of data, which amount to hundreds of petabytes of data, which have to be processed every single year at CERN. So the detectors which we have in the LHC are themselves marvels of technology. So we have 4 large detectors in the LHC, and in pictures, it's very, very difficult to give the scale of how big these things are, how big these instruments are. So maybe let's start with the Atlas detector. It's a 46-meter long detector with 25-meter diameter. It's a 7,000-ton instrument which sits 100 meters underground. So operation, maintenance, and design of this detector, it takes work of 5,500 people, and these people really work non-stop for this detector. Then we have a slightly smaller detector, Alice, which is 26 meters long, 16 meters in diameter. It weighs 10,000 tons, and it requires 2,000 people for upkeeping. The third detector, the CMS, is by size almost the smallest detector that we have because it's 22 meters long and only 15 meters in diameter. But by mass is by far the heaviest detector ever built. It's 14,000 tons, and it also, similarly to Atlas, requires 5,500 scientists to operate. Now, the last detector, last of the big detectors in the LHC is the LHCb. It's 21 meters long, 30 meters in diameter, 5.6 thousand tons, and it requires 1.5 thousand people to operate. So not all these detectors are the same. Atlas and CMS are what we call general purpose detectors. So they are designed such that they should discover everything which is happening in the LHC. ALICE and LHCb are more specialized detectors, and they focus on some very, very particular aspects of physics. There's actually the Atlas detector and the CMS detector, which produced the data which led to the confirmation of the Higgs discovery in 2013. So you might wonder how such a detector works. So when you collide two high energy particles, what actually happens is that this collision generates a series of new particles. And these new particles can behave and transform in very complex ways. And this can sometimes lead to decays into many, many more particles. So here you have an example of a high energy collision, or rather the outcome of a high energy collision, what happens inside of a detector. So all these lines and traces and color blocks, these are signals recorded by a detector due to the collision which happened inside of the detector. So to simplify things, you can think of a particle detector as a very high resolution digital photo camera. So the resolution of such a camera is in the order of hundreds of millions of pixels, and it takes billions of photos per second. So we need to take these billions of photos per second because the collision rates in Atlas and CMS are actually several billions events per second. So this is the rate at which we collide particles in the LHC. And why do we need such high rates? Because the physics which we want to study happens very rarely. So some of the events in which we are interested happen only once per 10 to the 14 times. So the probability of something interesting happening is extremely low. So then you need to produce lots and lots of collisions to be able to produce enough statistics so you can sieve through it and look for the interesting events. So this huge number of collisions, of course, produces significant amount of data, and this is a real problem that someone has to deal with. So the detectors, they produce data with rates in the orders exceeding petabytes per second. This is, of course, way too much for our computing needs, of our computing capacity to handle real time. So this data has to be somehow filtered. And each experiment or each detector does it in a slightly different way. But the general gist is that first, the raw data from the detector is passed to something which we call the hardware trigger or a hardware filter. And these are racks of FPGAs or dedicated ASICs, which look at the raw data coming from the detector and they make a decision in real time if this event is interesting or it should be discarded. So this step decimates the data by a factor of roughly 1,000. So we reduce the data rates to terabytes per second, which is still a very significant data rate. So then from the hardware filter, we pass the data to a more sophisticated software filter, which runs in a data center. And these algorithms are more sophisticated and more advanced, and they can take a more educated decision if a given event is interesting or not. So the data rates with which we end up in the end are in the order of gigabytes per second. So of course, in all this process, there are several caveats. The most important one is that all this data decimation must be done in a scientifically sound way. All this particle physics analysis, or this analysis of the detector outputs, this is based on statistical analysis. So you have to be very, very careful that by discarding certain data, you don't introduce any bias in your data. So there are literally hundreds of people who do nothing else but work on these filter systems or trigger systems. And another complication is that in the years that we call physics production, when LHC is really fully operational, these detectors operate close to 24 hours per day. So this system has to be extremely robust and close to maintenance free. So the data center, which runs the software trigger, is located at CERN. We call it the CERN data center. It has to sustain 24-hour per 7-day operation all year round, every single day. And its main job one of the main jobs is to process the hundreds of petabytes of physics data produced every year. So as any other data center on the planet, the resources are constantly growing. At the moment, we are somewhere close to 470,000 processor cores and 11,000 servers. So this data center constitutes what we call tier 0 of the worldwide LHC computing grid. This grid was conceived in the beginning of this century, and the goal was to come up with an infrastructure which will be capable of dealing with the amounts of data produced by the LHC. It's a hierarchical structure with tier 0 located at CERN, so the CERN data center. And this tier is responsible for storing the raw data, doing some data reconstruction, and distributing the data to tier 1 data centers. The tier 1 data centers are 13 high-performance computing centers located in the US, across Europe, and in Asia. And they are responsible for permanent storage of data, reprocessing of the data, and then performing some high resource need analysis. Then we also have tier 2, and these are about 160 sites all across the planet, so on each continent besides Antarctica. And these data centers are tasked with simulations and end users analysis. We also have an informal tier 3, but these are more like local institutes and even single user PCs, which can connect to tier 2 sites to extract some interesting data. So in total, the grid consists of 170 sites in 42 countries, and it provides 24-hour per 7 days operation. In total, it's a pretty significant supercomputer with 1.4 million cores and 1.5 exabytes of storage available now. The data transfers within the grid now peak at 3 petabytes per day. So all this is very nice, and as great as the LHC is now, we always have an upgrade up our sleeve. So this is exactly what we plan to do to the LHC, and between 2026 and 2028 is a major LHC upgrade, which we call High-Luminosity LHC upgrade, so HL-LHC upgrade. So it required us to already do a very complex upgrade of all the other accelerators that we have at CERN, so the accelerators which supply the beam to the LHC. And with this upgrade, we will produce much brighter beams, which will lead to more collisions. And these collisions will happen in detectors, which are upgraded. And all this will allow us to study even rarer events. And to just give you a sense of what we are trying to do, the yellow line on this plot, you can imagine that this is the integrated number of collisions that we had in the LHC since its conception. So this is when the LHC started. And this is where we are now. So over the next 4 years, we want to double the amount of data produced in the LHC over the last 10 years. However, after 2028, with the High-Lumi upgrade, High-Luminosity LHC upgrade, we want to gather the same amount of data over 4 years as we did in the previous 15 years of operation. So this is all really a significant upgrade. And projects like High-Luminosity LHC are a real innovation driver for a place like CERN because they require us to do a lot of R&D. So we need to develop more sensitive and faster particle detectors. We need much stronger magnets to guide beams. We need to show that we have unprecedented control of particles' movement to bring them into collisions. All these high energy beams, we have to protect the accelerator itself from the potentially dangerous losses of the beam. And also the power that we supply to some of the components is extremely high. And in today's times, the efficient power transfer becomes more and more of an issue. So there are many technologies being developed in scope of this High-Luminosity LHC program. And in this photo, for example, you can see that some of the components are already being installed in the accelerator. So these projects really stretch over several years. Now, all these extra collisions, of course, will have some consequences on the computing needs of the LHC. So it's not a surprise that we foresee a major increase of computing needs in at CERN. And there's a significant R&D ongoing, but not only to increase our capacity, but also to optimize the use of the available resources and possibly to integrate new solutions. So again, to give you some sense of what we talk about, Atlas, so one of the big experiments in the LHC, they made this graph with their foreseen annual CPU consumption. So we are in 2022 now. So by the time High-Luminosity LHC is operational, we talk about up to a 6-fold increase in the CPU consumption, annual CPU consumption. So over the scale of 6 years, this is a really significant increase of resources which is needed. So CERN is addressing this on multiple fronts. One of them is that we are actually building already a new data center, which this is a visualization of it, which you can see here, which will replace our existing data center, which has been in operation since 1976, I believe. Now, CERN is not doing all this R&D alone, especially in the IT sector. In 2001, we established something which is called CERN Open Lab. It's a very unique public-private partnership with a main goal for developing cutting-edge computing technologies for the global research community. So not only for CERN, but also for other research facilities. We collaborate here with many industry leaders. It's an extremely interesting initiative. I invite you to have a look on their website, what they are up to. It's really cutting-edge stuff. So besides R&D, the Open Lab also focuses on training of the next generation of IT experts. So they train students, they train engineers, they train IT professionals to be able to use and deploy all these new technologies which are developed within Open Lab. So Open Lab is run in stages. Every few years, they refocus on new areas. So they really try to follow the market trends. And in the current stage, the pillars on which they focus are exascale computing, artificial intelligence, quantum computing, and applications beyond particle physics. Especially this last point might be interesting because you would be very much justified to ask if CERN does something which is tangible for society. And I think a good example of this is the World Wide Web, which I think we all know and love. So the World Wide Web was actually initiated at CERN, and in March 1989, Tim Berners-Lee, who was a British scientist working at the time at CERN, he submitted the first proposal for the World Wide Web with the intention of making it easier to share documents and other resources within CERN and other collaborating instruments using the growing internet infrastructure. So CERN management saw the potential of this proposal, and by the end of 1990, we had the first web server, first web browser, and first website running at CERN. So many things happened in between. This was a very fast-growing technology, and CERN management had to decide what to do with this long term. And in April 1993, they took a very important decision, which I think impacts the society until this point, is that CERN gave up all intellectual property rights to the World Wide Web. So the licensing issue here was solved over the next few years until we arrived to the copyleft licensing for the World Wide Web as we have it now. But essentially, this decision made internet what we know it today. It's a free resource, or at least the World Wide Web. It's a free resource. So just to complete this story, Tim Berners-Lee left CERN in 1994 to create the W3C, well-known W3C, so the World Wide Web consortium. But he stayed friendly with CERN until these days. So besides World Wide Web, CERN has also other impact on society. And I think a very good example of this is medical applications of what we do. So the technologies developed at CERN and the research done at CERN in general. So one example of this is production of rare radioisotopes in some of the CERN accelerators. And these isotopes can then be used for diagnostic purposes or even for therapy. Some of the particle detectors which are developed at CERN, firstly to detect particles, then they find use in medical imaging. And this is actually more and more popular course of action. So here in the background, you can see an example of such a chip. Here it's called Timepix-3. However, for medical applications, this is called Medipix. So this chip is now used by many companies, and it makes it possible to perform full 3D color X-ray scans. But also just the particle accelerators can be used for medical applications. So, for example, hadron radiotherapy, so using hadron accelerators and irradiating patients with beams of hadrons, is becoming more and more popular. It's very popular in the US, and it's growing very fast in Europe as well. And this would not be possible without places like CERN laying the founding stones on how to operate hadron accelerators. And something which is the latest, newest addition to the medical applications is the so-called flash therapy. It's a very hot subject in radiotherapy now. This is essentially, if you go to an oncology conference, this is 50% of talks. And this is using very powerful electron beams to cure cancer with saving healthy tissue in a much better way than what is possible with any other method. So these chips, which find use in particle physics and then in medical imaging, they have also other uses. And here I have an interesting example, which I called cultural heritage. But there was a European company which developed an X-ray scanner using one of these detectors, which made it possible to rediscover a painting of Raphael, which was hidden behind canvas, holding another painting. So such techniques really become possible thanks to the significant progress done by the particle detector engineers and the development of particle detectors. So CERN is also extremely active in education, communications, and outreach. We welcome around 150,000 visitors each year, which are then guided by volunteers from CERN personnel. We guide them all around the site. When we can, we bring them to the accelerators as well. So this is how I ended up at CERN. We create every year hundreds of opportunities for students to come to CERN, spend 6 months, a year, 3 years with us, and use our facilities to finish their studies, to do their bachelor's, master's, PhDs. CERN also has multiple dedicated programs, for example, for high school teachers. or for engineers and physicists working with accelerators, but also for IT professionals. This very famous CERN School of Computing, which deals with a lot of issues, which I mentioned a little bit earlier in my talk today. So we do all this because we truly believe that one of CERN missions is to inspire and nurture scientific awareness in all citizens. And I hope that this is at least partially what I did with my presentation today. And with all this, I thank you very much for your kind attention.
Thank you, Michał, for taking us into CERN Institute and sharing, what good we can have with cooperation with CERN Institute and how we are changing the world. And I guess that we have 5 minutes for the questions, if you are okay with that.
Absolutely.
So, any question? Okay, so I'm going.
First of all, thank you for a great presentation. And I have two questions. First,
I'm sorry, I can't hear you very well. I'm sorry.
Hello? Can you hear me now?
Yes.
Okay. So thank you for a great presentation. I have two questions. First, technical. Second, you name. Can you hear me?
Yes.
Okay. Could you name one or two major hardware suppliers to the CERN?
Hardware of what?
I heard today about petabytes, terabytes, servers, processors. Major one.
This is not my domain, really. So I don't want to name any names, to be honest.
Okay, I was curious about it. Second question, what is your opinion about the idea that the entire universe is a simulation?
My personal opinion is also, I think the problem of theoretical physics is that, or the beauty of theoretical physics rather, is that it takes one person to make a theory, or it takes one person to make 100 theories, and then it takes thousands of people to try to prove this theory. So we have to be very selective in which theories we try to pursue and we try to investigate. I personally don't believe that the universe is a simulation, but we do science, so if I see proof to otherwise, I will stand corrected.
Thank you very much. The next question.
Okay, maybe it will be a bit political question, but let's try it. So Europe is facing the energetic crisis, which is coming at us, I think, from angles. And as far as I know, the collider is pretty much energy. Do you see any danger area that, for example, work on the collider will have to stop?
So of course, this is a real concern. Concern as we live in a society, as we exist in certain political and economical context. We are a public institution funded by member states, so we are not immune to what is going on in Europe. So CERN management already took a decision this year that operation of CERN this year will be shorter by 2 weeks to conserve energy. This was agreed by the local authorities and by the authorities responsible for energy in France and in Switzerland. This is deemed as enough for the moment, but we are ready to take more serious action if this is really necessary.
Thank you.
I have one more question related to organization, because you mentioned like 5 single door. So what methodologies, how are you using to organize this work?
Which work? Sorry, I didn't hear the beginning of the question.
There are a huge number of people working on this project. So how do you organize it? I mean, how do you organize the teams, people? Do you have any scheme, tools? How do you make all those people work together and achieve the goals?
It's sometimes you have a feeling it's a miracle that all this works together, especially when you see the number of institutes collaborating. It's 450 different institutes with different administrations, different legal frameworks, and different everything in many different countries. So it's sometimes it's a real sense of achievement that we managed to get it work. From the CERN side, so from the let's say accelerator side, we are organized like any other big organization. So there's a hierarchical structure, and we have clearly defined responsibilities: who's responsible for what, which group is responsible for which part. It becomes a little bit more difficult in the experiments when there are more institutes collaborating with each other. But we managed to get it work. I think 68 years of history dealing with science definitely helps with this.
Thank you very much. The time is for the last question. Oh, okay, we have.
Hey, Michał, thank you for your presentation. It's really great. I'm wondering regarding powering, what's the average monthly power consumption? And do you rely on public power plants, or maybe have some private ones? Or do you consider to have ones in the future, maybe?
So the average monthly power consumption, this is going to be in the order of 100 gigawatt hours, because now the yearly power consumption is 1.3 terawatt hours of energy. So this power comes mostly from the French network, from the French grid, electrical grid, but we have a backup connection to the Swiss grid as well. But we rely on public energy.
And any plans for the future to build your own power plants and be independent?
Not that I'm aware.
Thank you.
Thank you for the presentation, Michał. It was the last question. So take care and see you soon, I hope.